Hello everyone, I am Yihao Liu. It is a pleasure to share our CVPR highlight paper to you. Our work is entitled DegAE, a new pre-training paradigm for low-level vision. Recently, self-supervised pre-training has achieved remarkable success in high-level vision, but its application in low-level vision remains ambiguous and not well established. What is the primitive intention of pre-training? What is the core problem of pre-training in low-level vision? In this paper, we aim to answer these essential questions and establish a new pre-training scheme for low-level vision. To learn a general low-level vision representation that can improve the performance of various tasks, we propose a new pre-training paradigm called degradation autoencoder, DegAE. DegAE follows the philosophy of designing pretext tasks for self-supervised pre-training and is elaborately tailored to low-level vision. To begin with, let us have a retrospective to pre-training in computer vision. It is well known that pre-training is now prevalent in high-level vision. Why do we need pre-training? There are several reasons. Large models are data-hungry, especially for transformer-based models. To train such large models, large-scale data are required. However, manual labeling is very expensive and laborious. Limited data will lead to overfitting problem and unsatisfactory generalization. Hence, pre-training is proposed. There are three steps for pre-train fine-tune paradigm. First step, we need to design an appropriate self-supervised pretext task, like instance discrimination, mask image modeling, etc. Step 2, we pre-train the models on large datasets, like ImageNet. Step 3. Once we have pre-trained our model on large data, we can fine-tune the model on specific downstream tasks, such as image classification, object detection. To sum up, there are several key points in pre-train fine-tune paradigm. The designed pretext task is self-supervised without expensive labeling. The learned representations should be useful. The manual annotation of downstream task data is expensive. The pretext task is different from the downstream tasks. Now, let us revisit low-level vision pre-training. To begin with, we first analyze the characteristics of low-level vision tasks. According to the paired data acquisition process, we can roughly classify low-level vision tasks into two categories: low-cost and high-cost tasks. Low-cost task. The paired trained data can be easily synthesized by cheap operations. For example, SR, Gaussian denoise, Gaussian deblur. High-cost task. The data acquisition process is relatively expensive, resulting in limited training data. For example, dehaze, motion deblur. There are rare literatures focused on pre-training in low-level vision. A pioneer work, IPT, first proposed transformer-based pre-training model for low-level vision. During pre-training, IPT utilizes multitask restoration as pre-training task. The pretext task is the same as the downstream task, including denoise, dering, and SR. There are two problems. They all choose low-cost tasks for downstream fine-tuning, while there is no limitation in creating training image pairs. The objectives of the pre-training and fine-tuning are the same. The learned representations can only benefit the tasks involved in pre-training. We address such a challenge from two aspects: task selection and pretext task design. We claim to focus more on high-cost downstream tasks rather than low-cost tasks. Pre-training is more beneficial to high-cost tasks. Also, we design a more general and explainable pretext task for low-level vision. We devise a novel pre-training paradigm for low-level vision. Since the goal of low-level vision is to process low-quality images with various degradations, we propose a degradation autoencoder to achieve content degradation, disentanglement, and generation. DegAE accepts an input image with degradation D1 and a reference image with degradation D2. It attempts to transfer the degradation D2 of the reference image to the input image, obtaining an output image with input image content, but with degradation D2. The examples of degradation transfer are described in the figure. Through such a learning paradigm, the model is expected to learn both natural image representations and degradation information, which are the key components in low-level vision. The proposed paradigm is more reasonable and consistent with that in high-level vision. We conduct experiments on high-cost downstream tasks, including image dehaze, image motion blur, and complex image de-ring. For image dehaze, our method improves swing IR by 6.88 dB and uniformal by 3.22 dB. For motion blur, DegAE improves swing IR and restoral by 0.47 dB and 0.43 dB, respectively. For image de-ring, DegAE also improves the baseline over 1 dB. For visualization, with our pre-training, the model can produce more visually pleasing results. We also conduct experiments on low-cost tasks. The experimental results are consistent with our analysis. There are only marginal improvements on low-cost downstream tasks. Since unlimited training data weakens the significance of pre-training, as sufficient data can facilitate full training of the model. If we want better performance, we can simply enlarge the model size and the data size. That's all. Thank you.